Hello, everyone, and welcome back to the channel. It is Wednesday, and the crew is assembled with a special guest on this monitor, and I can't wait to introduce him to you. Well, not introduce, reintroduce. This is our 268th consecutive hangout in a row. The crew does not miss, and one of our really strong crew members. He doesn't get to join us every day because he's a busy scientist, but Daniel Sheikh, we lovingly call him the classifier to the stars, which means we're the stars. But he's a meteorite classifier and all-around great guy. He's decided to join us today in the 11th episode or edition of From the Lab with Daniel Sheikh. So, Daniel, it is an absolute pleasure to have you on the show and on the channel whenever your schedule allows, man.
Thank you so much, Topher. Really appreciate it. Thank you to everyone who's attending today or watching this video right now on YouTube, whenever that is. I'm really happy to be back here and to talk about such an interesting meteorite fall that occurred over the past couple months.
Yeah, good. You teased the subject, so I'll get it out there, man. We're talking, I heard it say Wadsworth, but you said Wadsworth. So we're going to have to get a correction on that one first off. But this is the Ohio eucrite it's a monomict eucrite, I believe, that fell the 17th. You're going to tell us all the details about it, but it is the Ohio fall that everyone's been going crazy about. We've had a few episodes on our show about it, segments on it. Now, this is not going to be a in-depth deep dive like the in-depth classification 3-part series that we had in the last session. We're going to do a brief one on this, as you said, but I wanted to ask you a little bit before you get into this, because this one is special. This is the American one. A lot of different pieces came together, and you were like the puzzle holder to those pieces. So I'm going to ask you to talk about that. But could you also talk about what you can talk about and why?
That's a great point. So yeah, there are a lot of moving parts involved in this, not just from the science perspective, but from many different meteorite hunters that were out there finding material, essentially doing the hard work. For the scientists, what we're doing, I'll just say it right now, it's the easy work, because going out, finding pieces is very, very difficult. And each and every person who found a piece of this meteorite and was able to add information to what we know about it, whether in the form of how much material fell, material that was donated for science. I'm very thankful and grateful to each and everyone who went out and found a piece. So, but regarding information, so because I was working in a large team of scientists, some data that was collected from other scientists is publicly available, and I can share that. But some of the information that was shared through email exchange or sort of things that pertain to things from a certain opinion on some samples, I'm not going to go into there because everyone has their own interpretation in a way of this meteorite when we were doing the classification process. And so I'm going to mostly speak about it from what is publicly available on the METBOL website, but also some perspectives I got when I was doing my initial evaluation of this using the instrumentation here at Portland State University.
Awesome.
And the other thing, just very briefly, that I will not also talk about, there are some people who found pieces of it that wanted to disclose the public location of where it was at. I made sure to ask for permission of that before that went into the strewn field map that I made. But then there were also some finders who didn't feel comfortable providing that information, so I was still able to include them on that map, but not including things like coordinates or when they found it. So I was trying to accommodate many different parties involved. So like you were saying, trying to fit all the puzzle pieces together and make sure that, everyone was content.
It sounds like me planning a meteorite mansion, 16-day trek and having people. No, I think that's super interesting. And that's really why we wanted to have you on this show to talk about a little bit of, first off, I alluded on a show recently that the struggle that scientists had, and please correct me, was this is a very expensive, rare meteorite and very, very hard fought for on the ground. So the people, as you said earlier, who generously donated to science, man, that's a tough ask. And you need 20 grams of this stuff. So is that what kind of the genesis was for the integration of many pieces?
Well, that was a part of it. And at the time when the meteorite first fell, I didn't think that it would be that large of an issue to acquire material, since historically in the past, even with meteorites like Tarda, which I've worked on with other people, and some other falls I've worked on, and even working on just NWA meteorite finds, several ungrouped achondrites, rare lunar meteorites, it never really was a challenge to obtain type specimen material. But the combination of that it fell, of course, everyone is asking about that fusion crust, how unique it is compared to every other meteorite out there. The classification, or I guess, knowing that it was some kind of, it wasn't an ordinary chondrite per se, like a lot of other falls were. So you combine that uniqueness with the fusion crust, with the fact that most of the individuals found were very tiny, sometimes
Yeah.
sub-gram, and there were only a few stones that were found that were larger than, let's say, 100 grams in size. And so really, the first couple weeks after it fell, trying to acquire material was very difficult. I will say that right now. I did get a little bit of backlash from some people after the classification was done, since some people thought that we would have trouble getting 20 grams. And then finally, when we submitted it, they noticed that there were more grams in the type specimen material. But that came much later. That came after several weeks of not knowing whether we'd even have more than 3 or 4 grams and trying to acquire material just to do initial analysis. So that came out to being a bit more of an issue than other meteorites. But again, there were so many circumstances that came together that kind of just made it a little more difficult. But I'm glad in the end it worked out and we got the material we needed.
Me too. I am glad, and I don't fault people for holding on to their little sub-gram pieces. If I traveled out there in the cold, I want it as well.
Oh, absolutely.
It does, and one of the reasons why, I'll just touch on it for those who may not know to what that repository, that deposit of meteoritic material is for. Once it's classified and known, it doesn't belong to Daniel. It belongs to his institution. It belongs to a repository where other scientists can ask for clean samples directly from the classifying organization. Okay, is that pretty much? I saw you flinch at a few of those words. So what did I get wrong?
You actually did a really good job there, Topher. So yes, the whole point of a type specimen is to ensure that, whether it be a year from now, 20 years from now, 100 years from now, that there is material available to be used for scientific research. Sort of in a way, if you want to think about it, think about the Apollo moon rocks that were brought back. Some of them have been opened and studied, but there's actually a subset of those samples that have still, to this day, not been looked at, because we know that moving forward as technology advances, we're going to have more instrumentation, better curation of equipment, and therefore we'll be opening them periodically and, eventually being able to learn new things about them. So in the same way, being able to preserve and curate these meteorites and keep them somewhere safe where there's a long-term objective to utilize these for science, that is what a type specimen repository is. It does not go into any of our pockets and go back to our house, I'll tell you that. It stays in the repository, and it's solely used to exchange with scientists who, let's say they need a piece, they contact the repository, we send them a piece, they do their research, they publish a paper, for example, and then of course, we get the piece back, or depending on what they use it for, they sometimes use it. So that's really what it all is for.
Fantastic, man. That was a great intro conversation to let people know the special circumstances behind this classification, because it is out of the ordinary to have a team of scientists and a team, please calling out for samples. It's usually one submitter trying to push your sample down your throat. So I appreciate you explaining why this is different. I'm going to turn it over to you. You have a presentation. We're on your schedule, and then we might have a couple questions for you afterwards. But please, man, we're all ears.
Sure, sounds great. All right. So this is episode 11, I believe, of From the Lab, and I'll be talking a bit about the Wadsworth Meteorite classification. So this is going to involve a bit of anecdotal storytelling, a bit of, I guess, discussing some of the interesting parts about the meteorite from, I guess, my perspective, since there are so many different perspectives of this meteorite out there, and talking a bit about the classification process from some initial work I did with some scientific jargon. I'll try not to go too much in detail, but I'm sure there's some people out there who do want to know about why it's a monomict eucrite, etc. So I will talk about that. I'm going to start just very briefly talking a bit about myself, since for those of you who have seen my From the Lab episodes, you might be a little more familiar, but for those who haven't, I started off as a meteorite collector actually out of high school. This was the first ever meteorite that I bought. This is 2.49 kilograms. It's a very weathered conduit. I probably wouldn't buy this again today. But I bought it on eBay, and I was studying geology at the time. I was an undergraduate student at the University of Florida, and I had done some research projects using the scanning electron microscope. So I was looking online, and I realized that, hey, I could classify this meteorite. I could cut this rock and find out what it's made of. And so from that process, I did some rudimentary work. I took a slice and I stuck it straight into the scanning electron microscope, and I was able to get some data. Looking back, I would not do this process, but this is how it started. And so from this, I was able to get my first classification, Northwest Africa 11838. This was over 8 years ago. This was in 2018 when I had just graduated with my undergrad degree in geology. And from this point, I've done, I guess, quite a lot of classification work, you can say, over the past 8 years. I've worked on a lot of different instrumentation from various scanning electron microscopes, various electron microprobes. I've collaborated with many institutions, and I've been fortunate enough to be able to work with so many people to acquire so many classifications. At this point, I don't really remember most of the meteorites I've worked on. I will unfortunately say that, but there are quite a number of memorable ones, several, of course, working with the crew. And there's so many people I have to thank. I'm sorry if I couldn't put everyone's logo on here, but none of this was possible. This classification work I did without the help of many different meteorite collectors, sellers, dealers, hunters. My first ever post on the Meteorite Club was in 2019 when I just started classifying samples. I believe I had 10 or 11 done. And I said, hi, I'm from Florida and I'm happy to classify samples for free. I got maybe like one comment, but since then, I've just been very fortunate to be able to work on so many cool scientific samples. And for me, that's not only helped with, expanding my own knowledge, because I think that working on meteorites through, actual looking at them up close and trying to decipher what they are, kind of like what a detective does, I think you can learn a lot more through that process than just reading a textbook, an academic book or something on meteorites. But it also introduced me to so many amazing people in this community. And it really emphasized my point that there needs to be a symbiotic relationship between meteorite scientists and collectors, which I think is absolutely essential for both parties to, moving forward to work together.
Wow, well said. I'm really glad you took the time to introduce yourself and give a little bit of background because I hardly ever do that, and you're so humble you never do that. And you're right. There's a lot of good friends on that logo chart right there. So I'm glad that you see a symbiotic relationship, that we have some good to feed each other.
Absolutely. And, it's important moving forward to, continue to have this. And so with this fall in particular, one of my goals was to make sure that the meteorite hunters, finders, collectors, their voice was also heard in this classification, that it wasn't just dominated just solely by the scientists or by, one party. It was sort of where everyone was able to contribute in some way to this in a meaningful way. And so as I go through this presentation, I'll talk about some of those ways. Now, classification for anyone watching on YouTube, if you're a geology student, if you're someone who is just very fascinated with it and you want to learn a bit more about it, it's a simple yet complicated process. I'd like to say there are some good papers out there that talk about how you classify meteorites or determine what kind of meteorite something is. These are two of those papers that I would recommend starting with. Um, they're not the easiest to interpret, but they are very good, I guess you can say, guides to have on hand if you are just curious about why something is one of these classifications. And, even though we continue to expand and there are several meteorite groups that have been added that aren't reflected here, I still think that some of these papers do a great job of just talking about the process. And before I talk about the meteorite, I just want to simplify that during the classification process, for those of you who might not be aware of what a monomict eucrite is, essentially it's what's called an achondrite. So generally speaking, we divide meteorites into what are called chondrites, meaning that when we started off with our initial solar system or solar nebula or protoplanetary disk as we call it, we had a bunch of gas and dust. We formed our early sun, and then we had a bunch of gas and dust swirling around it. From those, we were able to generate objects called planetesimals, which some grew in size through collisions to form protoplanets and planets. Some of those were broken apart and never really formed planets, but still kind of survived. We call those leftover materials chondrites. The important thing about them is a process called differentiation. That is that when an object is what we term molten, or in the form that it's been heated up so much that it's experienced a lot of melting, it can separate out to form a crust, mantle, and core. The Earth is a great example of that. Several other objects like the Moon, Mars are examples of that as well. But some objects are undifferentiated, meaning they have not undergone that melting process. So, typically we call them, of course, are chondrites. Now, the HEDs are achondrites, so they have experienced a differentiation process. And the meteorite Wadsworth that I'll be talking about today is likely coming from the crust of a differentiated asteroid known as Vesta, or from a family of asteroids called Vestoids, but most likely Vesta. So when I provide context on the geochemistry of this meteorite, just know that it is an achondrite and we call it an HED meteorite. And it's likely from the crust of a HED parent body asteroid. These are just, of course, some examples of our typical chondrites, as you can see. And then as I go into the achondrites, pay close attention to this example. This is mobility. This is a eucrite, of course, and you can see it's from the crust of this differentiated body. But that texture is very similar in some parts of Wadsworth. So just keep in mind, again, that Wadsworth is likely a crustal sample of a differentiated planetesimal. Okay, so now that I've just gone over a bit of that, before we go further, I do want to give some acknowledgments, for working on this classification. First of all, none of this was possible without the support of the entire Ohio Meteorite classification team. Several other classifiers were involved in this. For some, it was their first time classifying a meteorite. For others, they've worked on many other classifications in the past. But nonetheless, this was a very interesting experience for all of us to work together and be able to sort of contribute, some of our expertise and some of our experience with certain instrumentation into this. So this was definitely a team effort. Also, many thanks to everyone who was able to donate or provide type specimen material to any of the institutions. There was some, like I mentioned in the beginning, a little bit of difficulty trying to acquire material, but then towards the end, after we had gotten material, we then were able to get more material. And so that's why this number was a bit higher than what I initially thought it would be when we first started. But nonetheless, we were very thankful to acquire any type specimen material from anyone. So thank you very much if you contributed. And finally, I'd like to thank each and every person that contacted me or anyone on the team through Facebook or email, but because putting together this strewn field map, let me just say that I did compile this all myself, and it took way longer than I thought it would. I had to really, double check with every person I contacted. I had to, make sure that, when did you find this piece? How many grams was the piece? What was the mass you found? How many, or where was the location you found it? Things of that nature. And I had to make sure that I had permission from every single person who gave me, this information, because it would go in a public strewn field map. But at the same time, I did also get some questions as to, why this part of the classification was a bit short. The trade-off was that if I put every finder on here, that list would probably take 2 pages on its own. So the trade-off was here. I just listed people who donated type specimen to Cascadia. For the other institutions, it was up to them to decide if they wanted to list who donated material specifically to them. Some of them wanted to include that information in the strewn field template, which I did also add it in there. And then in the template, which I'll show later. There's a lot of other useful things you can find there. And you can use this with something like Google Earth if you want to go back out and hopefully try to find more pieces.
Yeah.
But yeah, there's a lot of moving parts, and I have to thank every single person on here for that. Finally, I do just want to talk a little bit about the Cascadia Meteorite Laboratory before I talk about Wadsworth, because one of the goals of the lab that has really helped me out since I joined as a student in 2021 was to promote meteorite research. And one of the goals of CML really is to have student-led projects on meteorite classification. We've had several graduate students actually talk a bit during the hangout. There's George, who did some work with sugartites. There's Vince, who has given some talks in the past. And this also was an undergraduate project he did looking at a newly classified Martian meteorite that I was overseeing, and he was able to present on this at a conference. And then he joined Portland State to work on his master's. So it was really a great way to bring students just to learn about meteorites, and we have the equipment necessary. And as more classifications are done, our collection has expanded. I've hopefully been able to contribute in some part to it, but a lot of the work that has been done was through my advisors, Dr. Alex Ruzicka and Dr. Melinda Hudson, who have really started this lab from the ground up. This wasn't something that was inherited like a large collection. This wasn't something that someone put a lot of money into. This was something that they both wanted to raise with the whole point of funding a new generation of scientists and to attract more people into meteorite research. And so I just want to end off with my acknowledgement to share that there are some goals of the Cascadia Meteorite Laboratory long term, and any donations would be appreciated. One of them is to expand acquiring more funds to do continued meteorite classification work, promote more student-led projects. And another fund is to hopefully be able to acquire enough funds to hire a full-time curator that would be in charge of managing that collection for essentially a lifetime, and make sure that that collection remains where it's at and that future meteorite research comes from there. So if there's any support you're able to give to the lab, this is our website, and please do so if necessary.
I do want to say that we had Melinda Hudson on our show. We did an interview with her, and she was a great guest, really talkative and just very conversational. And she went into a lot more detail about the history and founding of Cascadia. And there's a lot of pictures in media, if you don't like listening. But no, there's a lot of good information there about the organization and the funding that and how it gets used. So if anyone's interested, you can learn more by looking on our channel as well from Melinda Hudson conversation.
Yes, that's a great point, Topher. Melinda had a really nice talk, and she did go a lot more in detail on this as well. So definitely check it out, that video with her if you can. Now let's talk about Wadsworth. So how did we go from a meteorite that fell in Ohio to an officially approved meteorite known as Wadsworth? So again, for those who are not sure, Wadsworth is an officially classified meteorite. It's a confirmed fall. It fell this year on St. Patrick's Day. It has a mass of 1,728 grams, although that number has been slightly increasing as more pieces have been found. It's been classified as a monomict eucrite, and it was officially approved a couple months ago. And if you want to know more about this, I'll talk a bit about some of the classification processes and sort of how this came about. But if you want to know more, of course, this is all available publicly on the Meteorological Bulletin database. Okay, so when Wadsworth, so yeah, let me just leave this up here for a bit.
Yeah. Well, this is like putting
Just,
a putting
yeah,
a plate of barbecue down in front of us.
yeah. I'm just gonna leave this there for a bit. So
Wow.
obviously, this cannot do enough justice to the meteorite. This obviously photo credit goes to everyone who provided these images to me. These are all available publicly on the Meteorological Bulletin database that I put initially when I submitted this meteor. But there are many, many more images that just cannot capture enough how incredible this meteorite really is from a collector's perspective, just from an aesthetic perspective with, that COVID-19 image that, I guess continues to be sort of a very cool one. But let me just say that when the meteorite first fell, and there was a lot of attention on the news as well. Several, I think, news channels covered it. ABC, I think, had a video of it that it got over 1 million views. There was a loud sonic boom. There were videos, I think, of dogs that were scared by the sound of the sonic boom. And then there were some really cool interviews of people who found pieces. Associated Press also did a video with Roberto Vargas, Michael Farmer, and several other people. But when I first, so just a bit of backstory. There was a conference that around that same time. It was in Houston. It was called the Lunar and Planetary Science Conference. It's essentially a conference where you present on meteorite research. And I was going to go that year and present on some of my research, but at the last second, I was busy with something, so I didn't go. Had I gone to that conference, I normally turn off my social media and I don't pay attention to Facebook. But because I was at, here in Portland, I saw all these incredible images of this Ohio meteorite that were being found. And I was like, wow, that's incredible. And I said, is anyone working on this meteorite? Because one of the things that can happen is as soon as there's a fall, especially in the US, a bunch of hunters race, and I know that everyone is interested in finding pieces, but I also understand there is some level of competition there in, I guess, either finding the largest piece or finding the first piece or the piece that has the coolest crust. So, there isn't some inherent drive to try to find more pieces. And from a science perspective, you can argue that there is a similar thing where in academia, we have something known as publish or perish, which is sort of if three people work on the same research project, but one person publishes it first, they kind of get credit for it, and the other two, even if they publish after, might not get as much credit. It's a similar thing with classifications. It's an unfortunate part that exists, but it is out there. And so there obviously is an inherent nature. When you see something like this and you're a scientist, you're like, I've got to work on that meteorite.
Yeah.
But then you're also thinking in the back of your head, with how many people who have found a piece, how many other scientists are working on this too? And then what if we're all working on it at the same time? I mean, it's like those are things that like keep me up at night, when I work on this.
That would be a concern of falls of duplicate work, of scientific workload being duplicated very easily, because it's not like I'm going to run out and tell everyone I gave my 20-gram sample to Daniel and he's working on, like, everyone has their own classifier type thing.
Yep. Exactly. And and the thing is, I don't know with with the people who found pieces, I don't know if they sent material to other people. I don't know, they're really, I think one of the points that this fall really highlighted is that there wasn't that much open communication between, I guess, the collective group of scientists who classify, but also between the people who find pieces and I guess the collective group of people who classify in terms of just knowing where their material is going, just sort of that transparency. And so I said, you know what, I'm going to just be extremely transparent. And so, I mean, I'm sharing this because, it's an email I wrote and, I'm perfectly okay sharing it, but I emailed every single person in the US who does classification work. And I mean, everyone. And I said, hi, everyone, I'm sure we're all aware of this Ohio meteorite, pieces have fallen, it's likely this. I said, I have a feeling that pieces will be sent, and they were at the time. And I was happy to work on this material. My initial intention at the time, I said, I don't plan on taking charge, I'm just happy to collaborate with anyone. And if anyone needs, any sort of scanning electron microscopy work, since we had a scanning electron microscope at our institution, I'm happy to help out. I got a lot of replies from everyone who they got the same thing. Like, yeah, I have this piece being sent on the way to me, but I'm happy to also collaborate. And then it sort of ended up where everyone was saying that they had sort of some piece that was coming to them, but they didn't know who else was working on it. And they're only getting like a tiny gram and, they were happy to work on it. So that kind of drew me back to this other meteorite that I worked on together with a large group of people. This was Tarda. This was back in 2020 during COVID. And fun fact about Tarda, the only reason I'm actually on the classification is because I actually acquired the first initial piece of Tarda and I did the first analysis of it. That's why I'm in the geochemistry section. But really, I was just happy to work and collaborate with, so many other, established and, incredible scientists. At the time, this was 6 years ago, and I think I classified maybe like 90 meteorites at the time. I was still very, very young in my classification endeavors, and so I was just honored just to even be listed on this team. And of course, this ended up being a very rare meteorite, and everyone provided important expertise that led to a very cool abstract. Several publications have came out since, and of course, we formed our Tarda ACE consortium or Tarda Science team. But, thinking back to Tarda, I was like, wait a minute, this was a meteorite that so many people worked on. It was a very valuable meteorite. Why don't we do something similar to Tarda? So having that same mindset, I sent a follow-up email and I said, we're all interested in collaborating in some way. How about we form a consortium? We formed the Ohio Meteorite Classification Team, or the OMC team. And I said, not only will this strengthen the write-up, but having all of these different types of analysis can help evaluate things like getting better statistics, which is great in science. But also, since this looked like a breccia, are all the pieces that have been found, are they similar? Are there any differences between them? So in a way, it's kind of good that different institutions can look at different pieces, because then we can sort of say if there's any inherent heterogeneities within the sample. So then I shared a Google Doc. I said, all right, let's come up with all the roles we can work on for this meteorite, and then let's submit it together and sort of fill in these fields. So this really was a team effort from so many different people. My role, just to clarify it, I was sort of in charge of two things. The first was that when I acquired a piece of the meteorite, I was going to make some mosaics of it, of the thin section. I was going to do some SEM work to try to get some initial, details on the petrography of the sample, the geochemistry, and then I was going to send over my piece to another institution to collect follow-up work. At the same time, other institutions were also doing a similar thing. But another role that I had was working with all of the hunters through Facebook and trying to coordinate and get as much information as possible. So I really was in charge of gathering all this information and putting that into, of course, what ended up being the history section and the Streamfield template. So that was kind of parts of the roles that I had. One of the things that really helped out, and I have to thank Michael Kelly if he's on here, is being able to acquire a piece of this to actually do the initial work. So in our team, some people had samples of it that they were going to do analysis of, and fortunately, I got my piece at the same time that they did, so we were able to all do our analysis together, me and four other labs, sorry. And this thin section I got was thanks to Michael Kelly, who was able to make it and send it to me very quickly. And so a lot of credit goes to Mike. I put him on the petrography section because he did send me some really nice thin section images of the sample, which did help with some of my initial interpretations on knowing that this was a breccia, not something that was unbrecciated, which that was a question at the time when I was looking at some of the photos of Wadsworth. So I was able to put this into the scanning electron microscope, and I was able to get some of the initial data for Wadsworth that I did share with the group. Okay, so because I'm using a scientific instrument like the scanning electron microscope, I am going to talk just a little bit about the science behind it, because some of the images I will be showing, it is easier to understand how you interpret those images based on the instrument. So at Portland State University, which is where I'm at, we have a scanning electron microscope. This is what it looks like. The sample goes in this chamber right here, and we have several different detectors. The two detectors that I'm going to focus on is this one right here and this one right here. This is called the backscattered electron detector, and this is called the energy dispersive spectrometer, or EDS detector. Essentially, it's an X-ray detector. So how a scanning electron microscope works is you have a source at the top that generates a beam of electrons that are accelerated through all these lenses. They hit your sample, and when the electrons hit your sample, multiple interactions happen. Well, those electrons interact with atoms in your sample, and they can tell you many cool things about your sample, which we can use to make interpretations. The first thing that can happen are you can form what are called backscattered electron images that are essentially taken up into this detector, which is right here, or backscattered electron, or BSE detector. Now, how that works is these electrons interact with atoms of your sample, and depending on what type of atom you have, whether it's, let's say, an atom of iron or an atom of silicon, the size of the nucleus will vary because you're going to have more or less protons, neutrons, and electrons. And depending on that, you can generate different interactions. And so electrons that interact with the nuclei of our atoms but are elastically scattered back upwards and are picked up by this detector, we call them backscattered electrons. The key thing you want to note here are that for heavier atoms, you have a higher probability of these electrons being elastically scattered, meaning that we pick up more of them in the detector for locations that have areas that are rich in elements like iron, nickel, cobalt. So therefore, when I show you these backscatter electron images, anything that's bright means it has high density mineral phases that are made up of elements with high Z or high proton numbers, meaning elements that are lower down on the periodic table, like iron, nickel, cobalt, versus things that might appear dark, which are made up of elements that are at the upper part of the periodic table, like sodium, magnesium. So just keep that in mind as I show those grayscale images.
And Daniel, just to clarify, none of this is destructive in nature to your sample or to your thin section.
Exactly, yeah. These are what we consider as non-destructive techniques for inorganic samples. Obviously, for some organic samples, you can cause some damage. I guess you can say there are some minor things that can happen depending on what mineral you're looking at. So you have to be aware of what it is you're looking at with the scanning electron microscope. But generally speaking, for most rocks that we look at, which are made up of minerals like silicates, it's generally non-destructive. So there isn't any inherent damage that's done through this technique. So you can look at it with this microscope, and then you can take out the thin section or whatever rock you look at and send it to someone else to do other work, and there's not going to be damage that's necessarily done to it. So it's a pretty useful technique. And then the final thing that you can get is sometimes those electrons that interact with atoms in your sample can actually eject other electrons. Those electrons ejected are called secondary electrons. I'm not focused on that, but those can be observed with a different kind of detector. But when you eject interorbital electrons, in order to achieve a state of equilibrium or achieve a ground state, electrons from higher orbitals or higher shells will fill in that place. When they do so, they release an X-ray. X-rays are just energy, of course. They're a type of energy and they're a type of light. But basically, these X-rays have a certain energy and a certain wavelength to them. And it's characteristic of whatever this atom is. So if this atom is magnesium or this atom is iron, it's going to have a different characteristic X-ray. And those get picked up in this detector right here called the EDS detector. And that can basically tell me which elements I'm picking up and what their concentrations are. So essentially, what you can use this for is you can use the first detector, the backscatter electron detector, to tell me what the texture of my sample is. And I can make inferences on what minerals might be in my sample, but I don't know what they are yet until I analyze them chemically, and that's what this X-ray detector does. It provides me with their chemical composition, which then I can use to interpret what the mineral is, and I can learn a bit more about, well, is it a meteorite? And if so, what kind of meteorite it might be. So it's very important that both of these two interactions that we pick up with these two detectors provide a lot of information on the meteorite. Now I'm just going to leave this up for a quick second. So this is a backscattered electron mosaic of Wadsworth. This was from the thin section that Mike sent to me. A couple things. First of all, this is a scale bar. So this is 1 millimeter. So this is several millimeters in size. The first thing you'll note is it's in grayscale. So you'll have, of course, darker and lighter colors. Anything that's bright is made up of elements that have high Z numbers or elements that are, have high atomic masses on the periodic table. So anything rich in, of course, iron, nickel, cobalt, some other thing, titanium, they're going to show up here. Chromium. Anything that is darker tends to be material that is rich in lower mass elements like sodium, magnesium, silicon, calcium. And we can use this to assess maybe what minerals are present, but also to evaluate the texture. So a couple things I want to note here. How do we assess if something is brecciated or not? You'll notice that you kind of see this sort of look like that. You see a sort of large piece of something, and then around it you see a bunch of smaller things. This is one of the things we use to assess that there is brecciation. We have what's called a clast, which is just a rock fragment that's entrained in a sort of a finer grained or smaller grain sized matrix. And we know it's smaller grain size because of our scale bar. We can see that the sizes of these different minerals are larger compared to how they are here. Another thing you can use to assess this is we can see all these sort of dark veins cutting across here. These are fractures. While these objects are on their asteroids, how do you get them off their asteroids? That's by impacts. Impacts disrupt, they break up material, and they eject material. And so repeated impacts will break material, forming these fractures. It'll also compress material together, forming these breccias. And essentially, we can sort of see all that just right away from looking at the texture. So my initial observations when seeing this rock was that it was a breccia. I saw these clasts, I saw this matrix, and then sort of every now and then I'm seeing all these little smaller clasts. There are two distinctions. If you look at the Wadsworth petrography section, you'll see I mentioned lithic clasts and I mentioned mineral clasts or mineral fragments. Lithic means a rock clast. Rocks are inherently made up of roughly two or more minerals. So you can see there are two different colored minerals here. One is sort of this lighter color and one is this darker color. So this is sort of a lithic clast. And then you have these sort of isolated clasts of one mineral, like this one, or I guess you can say this one. So these are mineral clasts. So this texture is a bunch of lithic and mineral clasts entrained in a finer grained matrix. The matrix just refers to anything that holds together the clasts. The matrix can be, generally speaking, fragmental. It can be made of, which is just tiny fragments. It can be made up of melt, like if you have like melt that holds things together. In this case, it's fragmental, so just tiny little fragments.
Daniel, am I seeing something there on the right-hand side, a diagonal line going from like 11 o'clock to 5 o'clock, separating coarse material and finer grain? And is that scientific or anything to do with brecciation?
Oh, I see it. I see what you mean. Yes. So yeah, so when you have impacts, essentially, when you have an object that's, let's say you have the surface of an asteroid and you have an impactor that strikes it at, hypervelocity speeds like tens of kilometers per second, you generate so much energy, you form a shock wave. And as that shock wave propagates through these solid materials, it can lead to brittle and plastic deformation, which induces mechanical changes in the properties, forming fractures, forming these, like you were saying, these sort of almost like you can sort of trace it.
Exactly.
Yeah, that's a common thing you tend to see. In some cases, you get fractures that align themselves with some orientation to when the shock wave is coming in. So some people
Wow.
can actually interpret what direction, I guess, like, or where the sample may have been relative to where, if there was an impact somewhere, how the shock wave was propagating through and sort of what direction it may have gone. So yeah, you
Hmm.
can learn a lot of that
Fascinating.
with the looking at fracture analysis of heavily shocked meteorites. Yeah. Now, for those of you who are wondering what minerals are in this meteorite, well, I've simplified that for you. So this is, now we introduce that X-ray detector. And so that X-ray detector can generate things called chemical maps, where you take every single element, you map it to a certain color, and you say, okay, wherever that element is, put that color there. And the combinations of different colors together can give you what the mineral color would look like if that mineral is there. Now it can work it works in general, but it works better when the mineral has the same composition everywhere, because then it appears as the same color. If the mineral was heterogeneous in how these elements were distributed in it in different parts of the sample, the mineral will have different colors. But in this case, this meteorite in particular, you'll notice that it's made up of two prominent minerals. This sort of green mineral, which is a pyroxene, which is a silicate mineral. It's very common in earth rocks and meteorites. In this case, this is called low calcium pyroxene, so that green. Within that low calcium pyroxene, you'll notice there are these sort of these red lines that kind of transect through some small parts of it. They're a little hard to see here, but you can see them. Those are what we call exsolution lamellae, which means when one pyroxene transforms into two pyroxenes. And so now we have this other pyroxene phase called high calcium pyroxenes. So there's two pyroxenes here. Those are what the colors are, the red and the green. And then this purple, which you see very commonly. This is plagioclase feldspar. It's a silicate mineral. It's very common in earth rocks and in meteorites, well, some meteorite groups, especially in crustal samples and in eucrites. In eucrites, or many common basalts or cumulates from different asteroids or different planetary bodies, pyroxene and plagioclase tend to be the two most common minerals that make up basaltic rocks. And so in this case, I can see that they're the two most common meteorites by far, two most common minerals by far that make up this meteorite. So the other thing, of course, I mentioned is that you'll notice that the color of the mineral. So if I look at these pyroxenes, I look at the color, it's the same everywhere, meaning that
Yeah.
the composition of it is inherently the same. The same with the feldspar. It's the same purple color. There's no variation in color. It's roughly the same. Therefore, it roughly should be the same composition. So we call that equilibrated. In chondrites, the term equilibrated means that the mineral compositions have been homogenized so that they're roughly the same for the same mineral everywhere. And in this case, that is what's going on in this meteorite. So
Could that speak to how fresh it is, or is that in situ on the
So this
asteroid?
is this is a process that tends to occur on the asteroid itself. That's a
Okay.
great question, Topher. So on asteroids, or on Earth, you might hear about rocks. Like in a rock cycle, we have metamorphic rocks. These are rocks that have been subjected to high levels of heat and pressure. On asteroids, the pressure is very minimal. So therefore, a lot of this metamorphism, which would act to homogenize the compositions of minerals, is driven by heat. So these are thermally metamorphosed rocks that have been heated, not melted, but heated to the point that elements within a certain mineral will diffuse or exchange with that same mineral in different parts of the sample, and eventually it'll reach an equilibrium point, and you'll end up with a fixed, roughly homogeneous composition for that mineral. And so that's what's happened with the feldspar and the pyroxenes. They're all relatively the same composition. And as I'll show in a little bit, you'll see quite well just how
Hmm.
equilibrated this rock is.
Right.
Here, I just wanted to highlight the petrography section of Wadsworth. So again, I mentioned a breccia. Monomict means that the lithic clasts that comprise or compose the breccia are essentially the same. So when I go back here, you'll see that this lithic clast, they have roughly similar textures. They have similar modes, similar grain sizes of the minerals, and the same composition. So inherently, this can be deemed that because I don't see any other clasts that are different from these clasts, the term monomict is used. A good way to picture what a monomict breccia would be is if you took, let's say, something like, I don't know, maybe a chocolate chip cookie, and you had it, and then you crushed it up, but then you sort of smushed it together and you formed sort of this coherent like glob. That is what you'd call a monomict breccia, where you have some little bits of the cookie intact, and then some of them have completely split up and become very tiny. And you have all these small crumbs and big crumbs, and they're all kind of together. But it was the same material, it just was broken up. Those are cataclastic. We call that process cataclasis, when we break something up and then we reassemble it together. So this is a monomict breccia for that reason.
Those cookies example helped me out, so thank you.
No problem, no problem. Here, I'm not going to go into too much detail, but I just talk about the types of clasts in here. You can estimate modal abundances of different minerals by looking at, things like this. I didn't do that with this section, but some other classifiers did. And then, of course, we mentioned things like the textures of it. Of course, pyroxene and plagioclase are the two most common minerals, but we also mentioned that there are other minerals like tridymite, which is just it's a silica. Essentially, it's a polymorph, which means it has the same chemical formula as a mineral like quartz. So same chemical formula, SiO2, but different crystalline structure. So that's this dark red phase here. You can see there's quite a bit of it in this meteorite. They are very common to find in eucrites. And we also mentioned this exsolution lamellae of this high calcium pyroxene. Those are these lines right here that you see that are red within this green low calcium pyroxene host. You can see these lines also right here. I kind of zoomed in there, these dark
Wow.
lines here. You tend to get these a lot in rocks that maybe have undergone some degree of cooling, but not that much cooling. Otherwise, these would be pretty coarse. They're kind of thin. And then the other thing that we talk about we find things like chromite, which is this pink phase right here. It's an oxide phase, and it's very common in a lot of meteorite groups. It's an accessory phase. And something also that was interesting about this meteorite was the presence of iron metal
Hmm.
but not in the traditional sense you might think it is. So this is metal that is what we call nickel free, meaning that it's rich in iron, but there's very little or almost no nickel. So it's not metal that came from a chondritic impactor that maybe struck the surface of this asteroid. This is metal that was likely produced endogenously within the object, within the planetary body itself. And because of how fresh this meteorite was, this was actually my first time observing this phase in an HED meteorite. Before, I used to always see like weathered metal or
Mhm.
sometimes hydroxide phases. But when I saw this phase, I was very curious because I actually hadn't seen it before. And some other people who were on our team who they do research on HED meteorites, they were able to tell me a lot more about the fact that you can actually have this as a phase that forms in the interior of Vesta and some of these asteroids.
Wow.
So it was a great learning experience for me. I learned a
Yeah,
lot about it through
that's
how
super
fresh.
cool.
Yeah. And then the final section I'll talk about is this geochemistry section. So there were many labs that worked together on providing data. So on the right side, this is what's called a pyroxene quadrilateral. What that means is you take the low calcium pyroxene, so this green pyroxene, and then you take the red pyroxene, that's the high calcium pyroxene, and you plot their compositions on this. It's originally a ternary, but it's been cut into a quadrilateral. So essentially, anything that is rich in magnesium will plot here. Anything rich in iron will plot here. And then this way leads to compositions that are rich in calcium. So clinopyroxenes that are calcic, like augite, will plot here. And low calcium pyroxenes, because I say low calcium, they'll plot here. Now, essentially, these fields, these gray and these gold fields represent where different types of eucrites plot. Eucrites can be geochemically divided into what are called basaltic eucrites and cumulate eucrites. That inherently doesn't always apply to the texture. So basalt, generally speaking, refers to most people think of them as fine-grained, extrusive volcanic rocks, and cumulates people think of as like coarser-grained rocks. Essentially, what's been found are that basaltic eucrites plot here and cumulate eucrites plot here. But essentially, if your composition plots in these fields, you likely have a eucrite for pyroxene. When we plotted all four of the lab's results, I didn't put my own because I just put those that were measured with the microprobe. They overlap quite heavily, which fits with the fact that I was saying earlier that this is equilibrated. So the mineral compositions are essentially going to be very, they're not going to vary that much. And this was confirmed. So this was the cool thing about having four labs
Yeah.
investigate four different sections, is that because they were all in the same location, that also confirmed with fitting that this was likely a monomict eucrite and not something like a polymict eucrite. Because if we had other eucrite clasts, we would expect them to plot sort of everywhere here. But because
Yeah.
we're just in this narrow region, it fits with our monomict eucrite observation.
Mhm.
So that's something you can do with the chemistry of the minerals. The other thing that's been done is oxygen-isotope work. I'm not going to describe this in detail because that is a whole nother lecture. But basically, you can take the isotopic composition of an element like oxygen, which has three different isotopes, oxygen 16, 17, and 18, and you can plot them on a three isotope plot. And basically, what's been found is that different meteorite groups plot in different places. And HED meteorites plot in a very specific place. And so when you take the composition of an unknown meteorite and you compare it to HED meteorites, if it overlaps, then it's a good fit for being an HED or a eucrite. Now, this diagram right here on the METBL website, you'll notice that some of the crosses, which are where the data are, like one of them right here overlaps with this EFL. This is called the eucrite fractionation line. But you might notice that some of them kind of plot a bit off of it. This is a bit of a I guess, interpretation here because this line through more research work has been updated and more samples have started to be plotting here. So just know that if you think this is anomalous or plots off of there, it actually doesn't when you compare this meteorite with a bunch of other eucrites that have been
Yeah.
studied more recently. So it is an HED. It doesn't, just because this might look like it plots off the line, it's not anomalous. That was a question we did have initially
Mhm.
was, is it an anomalous eucrite? But when we took all of the eucrite data from the METBL and we plotted this meteorite, it overlapped quite nicely in that HED field. So it does
That's
fit with
awesome.
HED meteorites. So
That's a good call out because I was looking at that going, what's going on?
yeah, yeah, that is That's exactly. That's one of the things that I did get some people asking me about, like why does it plot off here? Why is it not anomalous? But
Mhm.
just wanted to mention that. So yeah, so you take all of the work that all of us work together, and we end up with this classification as Wadsworth. So yeah, it was a tremendous effort from all of us, and again, it's always great to have multiple opinions when you're trying to come up with a classification on something, because some people might think about something that you don't consider, and some other people might have expertise looking at something else. So really, that was it was good because I feel like we collectively wrote a very strong, write-up that might not have been as good if only one or two of us worked on it. So it really took a team effort on this one. Now, getting to that Sternfield map. Okay, so this took a lot of, help from many different people who hunted fragments. There were 126 stones on here, and I do have to go back and make some changes. So if you have found if you're watching this video right now and you found a piece of Wadsworth and it's not in this Sternfield map, please contact me. I have one chance to update this map before I can't change it anymore, and it's officially set in stone. So if you found a stone at Wadsworth and you want to include it on there, I can include it. Just please message me right away. Now, so far, if you want to access this map on the main write-up, there's a page called Sternfield Map. You click it, and then it takes you to all the members, and you can plot them in Google Earth. And so on Google Earth Pro, which I have on my desktop, it'll bring up something like this. And what you can do is you can look at each of these numbers, and you'll see that they're all here. And you can click on each of them, and it'll tell you what the mass of the stone is or any information about it. So it's really cool if you're trying to get a sense of just trying to look for like things like larger stones, or you're just trying to just understand how large the Sternfield really is. So I think that it was great that it was done for this specific meteorite, but this isn't something that's normally done for most falls. I will say that, just because it requires so much coordination from so many people. But I'm very thankful to everyone who provided me with information on this list. So fortunately, it brings out a nice Sternfield map for anyone who wants to go out there today and hopefully find a piece. I know the largest stones were found down here, closer to Rittman. So if you're feeling lucky and you want to try to find that multiple kilogram piece that was supposedly fallen somewhere here, I wish you all the best of luck.
Wow. Hey, Daniel, I have a question for you, and this may be out of your wheelhouse, but
Mhm.
I'm going to ask. I'm Gunsta. Very little recovered material,
Mhm.
not through a lack of effort. There's been a lot of hours and miles walked out there collecting tiny subgram ones.
Mhm.
So there may not be much more collected. So we kind of know the weight. What, about 1,700 grams, something like that. Do you have any impression or idea of the incoming mass before ablation?
Mm. That's a great point. So in the history section, so I don't personally have, but some of the people I work with, like Dr. Mark Fries, who works at Johnson Space Center, he works with the radar group over there, and they're in charge of essentially, they can do a lot of cool things, which also involves estimating the size of the meteoroid as it entered the atmosphere.
Mhm.
And I believe we wrote it on there. I wasn't sure how many feet we said in diameter, or that he wrote it was in the history section, but it was, I'd like to say, between 6 and 10 feet in size, the original object, I think somewhere like there. So what you can do is you can interpret the size of the object, and then you can, based on, you can calculate roughly what the density of the rock might have been. And you can sort of try to get a sense. So like if you know a length of it and you assume it's like a sphere, you can calculate the volume. And then if you can
Mhm.
calculate the density by the modes of the minerals, you can then find out what the mass of that whole thing would have been as it came in. And then you can kind of
Mhm.
compare it to what's been found and realize how much of that was lost in the ablation process, or due to people not finding more materials. So
Mhm.
that's one way you can do it. It's purely mathematical, but I believe we do list the incoming size of it originally. in the, I think the longest dimension at least. Yeah.
That's phenomenal. We were talking a little bit about the trajectory just now, so I'll piggyback on that. The very first pictures you showed of this thing are the coronavirus one. The fusion crust on this speaks for itself and is a standout among all meteorites, basically. Maybe one or two on record have the same features. Is that a result of the absolute perfect ablation entry process? I see you laughing. Or is it chemically? Because this thing, there wasn't many ingredients in this meteorite. So why do you think the crust was so unique on these samples?
Oh, that's a very loaded question, Topher.
Mhm.
So I will say, first of all, I'm not the right person to be answering this question. I don't study fusion crusts very well. I think a lot of collectors or finders actually would probably come up with a better answer than me because I really focus on the inside of the rock, not the outside. But and I will say that there is a group of people from the Natural History Museum in New York that just published a abstract to the Meteorological Society Conference annual meeting this year. It's in the program, I believe, and they actually talk about the unusual
Mm.
spiny fusion crust of Wadsworth. And I've been messaged by many different people asking, like, why is the crust looking like that? Or, that crust is, so impressive. Um, all I've found from literature is that those like spines, or I guess however the term is used for those, that it requires very specific conditions to get those. And obviously with how fragile, this object is, it's a very friable, material
Hmm.
also when you try to cut it. I'll just leave it off that you require specific conditions where you have to ablate the material in some way, freeze it in place, but not necessarily separate out, melt droplets from the ablating mass that would have to still be connected. So it's like, let's see, if you go to Hawaii and you see some of those lava flows and you take out like a piece of it and you hold it up like this, and as it's like drooping down, it's like solidifying, you'd have to hope it solidifies before a piece falls off, right? So I guess what that means is that it has to rapidly quench faster than individual droplets come off of the object. That's like
Holy
the
crap.
best thing I would say, which
Wow. That really puts in perspective right there, that visual.
has to be very quickly. That's all I can at least like. Oh, I would probably say with that, yeah. But in terms of the composition of it, it's mostly made up of pyroxene and plagioclase, which
Hmm.
most of our basaltic meteorites are. And so I wouldn't say it's unique to the composition, but I will say probably something about, the conditions when it entered, either the velocity it was traveling at, the angle of entry, how friable the thing may have been before, as it was coming in. There's so many things that probably
Yeah.
had to go right for this to happen. That's all I'll
Wow.
say.
Well, I won't make you postulate any further. Thank you, man. I appreciate it. We're going to take a small break right now. All right. We had a little bit of a break for some water. We got our questions together, and I'm just going to throw it to the crew members who have the questions. Travis, you're number one. Go for it, buddy.
So Daniel, you presented some awesome information. Thank you very much. So it seems to me Wadsworth was classified pretty fast. On average, how long does it take a classification to be completed? And if you're working on multiple classifications at the same time, how do you determine priority order?
Thanks, Travis. That's a great question. Well, that was a multiple part question. So for Wadsworth specifically, there was an incentive to get it published quickly because a group from the Natural History Museum, or I guess the AMNH group, they wanted to get an abstract out for this conference, the Miracle Society annual meeting, which was hosted in Germany this year. But there was a deadline that they had to get it out by May 5th. And traditionally, there is a deadline that you have to have a meteorite submitted to the nomenclature committee by a certain deadline before the abstract deadline, in order so it can be approved in time because it has to be voted on by the large committee of NomCom, and that can take a while. Unfortunately, in this case, because there were so many people working on the classification, I wanted to make sure that we all had time to work on the sample before I submitted it, but that would also mean that it would fall after the April 5th deadline for when new meteorites needed to be submitted by. So this actually was submitted by, I think it was April 17th that I submitted it, but I requested an emergency vote from NomCom, and they managed to approve it on May 30th, which was a few days before. So then now the Natural History Museum was able to submit their abstract because you can only submit scientific you can only publish a paper or write a scientific abstract on officially approved meteorites. You can't write it on meteorites that aren't approved yet. So there was a process that needed to be done, but I had to make sure that our group stayed to the process, that all of us worked on it, but that we had the assistance of NOBCOM to get it through in time to help another scientific group for their work. So that had to go by quickly. Obviously, there was a lot of communication involved. Traditionally speaking, with most classifications, if it's, they generally, it mostly depends on several factors. The first is the sample that gets sent in for classification needs to be prepared in the right sort of format that it could be analyzed, so like a polished thin section or a polished 1-inch round. The company I work with, Spectrum Petrographics in Vancouver, Washington, they do a great job of thin sections, but they take, generally speaking, weeks to months sometimes to make those thin sections, and they're usually backed up because they have a high demand of many other geologists across the US who send them stuff because of how well the job they do. So the other thing is getting time on the instrument. So we have a scanning electron microscope in-house at Portland State University, but there are a lot of users who use the instrument, and so finding the right time to use it is important. The samples also, require a little bit of prep in advance, so that also needs to be scheduled. And sometimes the instrument is down for periods of weeks or months. And so if you imagine that, I have 10 samples, let's say I'm going to work on over a period of a week, and then the instrument is down for several weeks, but I'm getting more thin sections back, then that builds up. And then it ends up being some cases where I have a backlog of samples that I have to get through. So it does take longer for some. So there's no specific, I guess, amount of time it takes, but roughly speaking, the two main factors that determine how fast something can get analyzed are availability of the instrumentation and making sure the sample is prepared in the right format to be analyzed.
All right, thank you very much. Next is Dave Pinsky.
Now, this turned out to be one of the most friable meteorites I've ever seen. If you just look at it, you have micros. Did that complicate the classification in any way?
Thanks, Dave. Yeah, that it definitely played a role. So when we were trying to get some type specimen material from one of the hunters who found a relatively large size stone, while cutting, there was a problem, and so I was initially supposed to get a few more grams, and it ended up being quite a bit less because the material was breaking apart when the saw was cutting it. So that played an issue for that reason. Another thing it played an issue with is when you have very friable samples and you're making a thin section, sometimes some pieces can sort of pluck out where you don't see them in the thin section when you analyze them. So in some of the images I showed, you might see there's like these holes, and that also fits with, it's friable and it's breaking apart as you're trying to make a flat polished surface. And then the other thing it likely played an issue with also was, obviously, in terms of if you're hunting the meteorite, and it hits something and it breaks into a million pieces, when you're trying to make a thin section, you can't really do it on powder. It's very difficult. So I received a vial of, I think, like 1.5 grams of just powder, and I can't make a thin section of that. I mean, it still counts as type specimen material, but I can't do much with it unless I'm going to dissolve it in acid and do like a bulk, measurement or do isotopic studies. But for making a thin section, I need a piece that's coherent enough. So yeah, there was some factors obviously with the friability of it.
Great, thank you. Great presentation. Thank you.
Daniel, I have a question about those. I was going to ask, was there one unlucky scientist who had to get a fusion crusted sample and crash it into a powder for one of those tests? Would you, if you were to do one of those destructive tests where you crush it into a powder, would you do it on powdered material that you already have, or would you do it on a crusted sample so you have crust in there as well?
That's a great question, Topher. Firsthand, you never want to, ideally, you want to only look at what's inside the sample because diffusion crust has its own composition that can, it has its own chemical composition. So if you're doing a analysis of the bulk chemistry, when you put fusion crust in there, it can sort of change it a bit than what it would be. The other thing it can do is it can do changes in the isotopic composition, because right where that fusion crust sample margin is, even though it's very tiny, there are some changes that go on as the sample is heated, to a very high temperature where you then form that glass and it starts ablating. That can induce very small chemical and isotopic changes. So the thing we always talk about in science is you want a piece from the inside that is free of fusion crust, and then obviously you know, if we're doing oxygen isotopes, you want to make sure you're doing it on a representative piece. So, you know, finding different crumbs and then crushing them up and then, you know, analyzing them, that is a destructive process. But, you know, the benefit of doing that also with a powder is the powder itself, if it came from a large stone, is very representative too, because you have all these very tiny pieces of the stone that are mixed in, but they're in a powder. So it's like you get the average of everything. So there's different approaches, yeah, but no fusion crust. You unless you
That's
specifically
amazing.
want to study the fusion crust
Yeah.
for most isotopic and chemical work, you do not want fusion crust in your sample.
Well, guys, late breaking worldwide news: Daniel Sheikh hates fusion crust. I don't know what to say. Allison, we're going to you.
One of the things that I remember most clearly about Wadsworth and the day that it fell was seeing that amazing fusion crust. And one of the predictions that I had out loud made was that we're going to be writing papers about this fusion crust for a long time, and that it was possibly even going to change what we know about meteorite fusion crust. Did it do that? And if so, how? And maybe it wasn't that was fascinating to you, but something else. Is there anything that's like rewriting the books about this piece?
That's a great question, Allison. So I will say that already there's so much interest in the scientific community in that fusion crust. There's several people, the group I mentioned, the Natural History Museum, they're using a technique called micro CT or XCT, which is you just a CT scanner, but you're putting a rock in there, not like, you know, like a human. And so what it's very useful is you can, you know, you can essentially get a 3D reconstruction of the object, including the fusion crust. And then you can run simulations with software and try to replicate that, and then use the 3D model as like sort of like how you get that. And then obviously you preserve it, right? You preserve the record that is what it looked like. So 50, 100 years from now, maybe you know, even if the rocks dissolve or break or something happens, we still have that record that the fusion crust had that shape. And so, yeah, there's several people who are interested in just how that crust formed. And there's already an abstract that's, you know, sent for that conference on the unique spiky Wadsworth fusion crust. So I anticipate in a couple years there's going to be a publication or two on this meteorite from
Right
someone.
on. Right on. Thanks, Daniel.
That's amazing when we can. I mean, I say we're part of the scientific discovery. Well, we're on the back bleachers, but we have really good binoculars. We have a question from Ken Wojcik.
Hi, Daniel. I appreciate you being here. My question would be, what would you suggest to keep this meteorite specimen fresh as day one in a display case in the Midwest?
That's a great question, Ken. To be honest, I'm probably not the most qualified to answer that question because I don't have that much experience with things like cold curation or working with, you know, like nitrogen-filled desiccators. But what we do at the Cascade Meteorite Laboratory is we have these auto desiccators that we store samples in to keep them at low humidity. And we've also put in packets of silica gel that we've heated and made sure that, you know, they're dry desiccant. So we do those two in combination to try to keep as much moisture out. In the Midwest, I'm not particularly sure how much that'd be different from somewhere like the Pacific Northwest. Maybe there are some differences, I would imagine. Or if, of course, if you're in Florida with, you know, high humidity. But just from what we do, just desiccator, cabinets, you know, silica gel. If you want to go the professional route and you can afford getting a bunch of nitrogen tanks and, you know, pump it through, that's another thing. But I'm sure there's a lot of other opinions, probably even in this hangout, that are much more qualified than me to talk about this. I don't do this actively.
Okay, thank you. I thank you for your time.
Thank you very much, Ken. Our final two questions are about more of the classification process. So this is really the last time to talk about the meteorite. So I'm going to jump in with my last question of the night. It's about the meteorite. We've been talking about its friability all night. And it's known that you'll never see a slice of this stuff. Like, no one's, we would say no one's that bold, no one's that stupid to try to slice this thing. Why do you think that is? There's a litany of reasons that were floating around in the chat. But I'd like to know, do you have, is it just one of these things where, like here on Earth, we have granite and we have talc, and we just happen to receive a talc rock from space?
Well, Topher, I think that it coherently goes into sort of how the rock itself formed initially. So, of course, it's a breccia, so it's made up of clasts that are held together by this matrix. If the matrix isn't strong enough to hold together the clasts, meaning if it's fragmental, if there's not a lot of melt in the matrix, if it's porous, right? So there's a lot of void spaces, and you combine that with the fact that we have impacts that can essentially, turn a rock into regolith, right, on the surface of the moon, asteroids like, when we went to Bennu, etc. You can imagine that over time, porosity goes up, and the friability goes up too. So it just has to do with the fact that the matrix is not very good at holding those clasts together. It's just relatively friable. And that's kind of just how we define it. There's a lot of grain boundaries with fractures between them, between different minerals. There's not a lot of, I guess, coherency in that kind of rock. And one of the best things you can use to, I guess, when you have things like friable materials or highly porous materials, if you want to really cement them together, you have a process called, let's see if I remember the name here. Ooh, sintering. Sintering is a
Hey.
process that you can do on things like lunar regolith, where you can essentially make it more compact, and you essentially have very tiny lenses of melt and a solid state, mineral growth like oswald ripening that keep things bonded together. And then, of course, you also have melt breccias. One of the really cool things about lunar melt breccias, when you try to cut them, they cut quite nicely compared to some of your fragmental stuff. Why is that?
Yeah.
Because melt is very strong at holding together things. It's like the
Mm.
ultimate cement. It's like when you freeze
Wow.
something in lava versus you freeze something in a bunch of like crushed up sand, right? Even if you wet the sand, it's still not going to be as coherent as something like a melt would be. So
Wow.
silicate melts
Fantastic.
are very, very good at keeping things together. But when you just crush stuff up, but you don't induce melting, you don't induce sintering,
Yeah.
you don't have slow
There's,
cooling, it's gonna just break up, most likely.
there was shock, but not significant enough shock to cause that melting that we
N-
need.
n- not enough post-shock heating. The term we use is when you have a shock event and you raise the pressures and you raise temperatures. The duration was short, and the amount of post-shock heating, so how hot the sample was at what temperature it was at after it was heated by the shock, meaning you broke it up, it was in sort of this heated thermal blanket of just ejecta. How hot that was, it probably wasn't hot for very long to undergo any sort of sintering process or solid state grain growth.
Awesome. Well, that helps me understand a little better. So thank you. I appreciate you going into that. That's the last boring question about the meteorite. Now, we have Dr. Chris Sanders wants to ask a question about how the classification went a little bit more too.
Yeah, hey Daniel, glad that you're here. I tell you, anytime you're talking, whether it's here or elsewhere, it's must see TV. So I appreciate you and appreciate your time. I've got a two-parter for you. Number one, as far as the classification process goes, and having so many different researchers involved, is that a matter of several people doing kind of the same classification processes or steps and then comparing notes afterwards? Or is each person doing an individual task and then other people are reviewing it? That's the first part. The second part's a lot more fun. You've got access to all these meteorites now. Do you still collect personally? And if so, what sort of things do you focus on with your collection?
Thanks, Chris. First of all, I really enjoyed your video, 5 interesting things about Wadsworth. I really enjoyed watching that, especially with seeing some of the points that you made. And
Thank you.
so the first part of your question, a lot of the classifiers who do classification work, really we kind of do sort of the same thing. We make thin sections, we look at them with a scanning electron microscope or an electron microprobe. So most of the people on the team who analyzed pieces of it used a microprobe. So when I showed that pyroxene quadrilateral and I showed the data points, those were all collected with the same instrument. So same instrumentation, same technique, but by different people at different institutions. So part of that was, I guess you can say, because we wanted to compare our findings to see if there was any heterogeneity in the stone, because if there was and it wasn't monomict, that changes our classification. All of a sudden, we might be into brecciated eucrite as the classification instead, or eucrite breccia. The other thing is we all really wanted to work on this classification, but we had to find some way that we all could feel like we were a part of it. So, if So, I mean, really, you could say that, one group could have collected the data and then everyone else could have, I guess, just sort of helped interpret it. And then maybe someone else, of course, like at UNM, they did collect oxygen isotopes, which was something that they were exclusive in doing. So that was something that they were able to contribute on top of everything else. But in terms of, did we need 5 sets of chemical data on the minerals? Probably not. It probably was overkill. But at the same time, did each of us who contributed to that feel that we were actually involved in the process and not just put on and, going along for the ride per se? So I really wanted to make sure all of us were satisfied with the job that we did. We all made our own interpretations of it independently. Then we brought it together and we formed that consortium and said, all right, how are we going to do this write-up? Do we all agree with what we think we found? And that's sort of how, I guess, that sort of went together. Yeah.
Awesome.
And then the other part of your question, so in the past, I used to buy meteorites on eBay. I used to do a lot of collecting. But then when I started classifying, one of the things I was told right away is that, especially, and I'm not going to call anyone out here, but it is a conflict of interest to classify a meteorite and then sell it. By far, it's a huge conflict of interest. I was told this in my second year when I was classifying meteorites. And, once I learned this message and I realized that, it's not a good practice, I just said, you know what, I'm just going to classify meteorites. I'm not going to be involved in the buy and selling part, even though, I think it's fun. I think the business of buying and selling meteorites and trading, I think that's really cool. That was what got me into it when I was younger. But now at this stage, I have to focus on it from more of a scientific perspective. So I think Lawrence Grossman, when he gave a talk on here, he talked about that he doesn't own any meteorites, and some other scientists came on and said they don't own any meteorites. I'm not going to say I don't own any meteorites. I do own meteorites, but I like to only own meteorites that are relevant to my research. So the ones that I do own are lunar meteorites and ones that contain a lot of pink spinel, because in the future, if I plan to do research on them, I have the samples on hand. I can, take them with me and do research. So if it's a research sample, I like to go on that, but I don't do any of this buying, classifying, and selling. I don't do any of that.
Awesome.
Just putting it out there.
Thanks, Daniel. I appreciate you.
A classifier should not do that. That's what I will say.
Yeah, because I classify it as a 1 of 1 from Pluto.
Yeah.
This is a great fall because it really, like you said in your presentation, it got a lot of news attention, and all those finders, all those people who participated in this. I was really tickled pink to see a lot of the Knowledge Bolide crew members' names in the write-up, and I happened to see Marissa's name in there. So we are finishing with a question from Marissa, but I want to give her congratulations for getting your name in the Met Bowl on such a beautiful meteorite, Wadsworth.
Yeah, thanks, Topher. It was an honor to donate a sample to Daniel and to go out there and find these meteorites. I couldn't ask for a better meteorite.
Yeah, thank you so much again, Marissa. That piece you sent, I'll be honest with you, that is the best piece that we have in our repository of Wadsworth. We've received several other pieces and vials of dust, but your piece is the only one that's that large, that's that intact, and that has that really cool crust. So thank you again. Melinda, when I opened the package, she saw it and she was like, whoa, and she looked at it and she was very impressed by that small piece. So, even though it was only 0.7 grams, that is absolutely essential. Every half gram, 0.1 gram, that mattered heavily in this classification. So thank you to contributing that. Thank you also, Pat, for helping out with that too. I know both of you also worked with that. And I don't know if anyone else is on here, but Carl Dietrich, Brett Cohen, Matt Stream, who I am going to add because he did contribute some material later on, but I will add him to the people who did contribute to Cascadia. Thank you again for your donations.
Awesome.
Thank you very much.
Awesome.
Yeah,
That's
Brett,
wonderful.
yeah, and Brett actually joined, so hello to him. Marissa, I don't want to cheat you out of your question.
You
got a
go,
question.
girl. That's so awesome.
All right, so my question was, with future US falls, do you plan on doing this again with reaching out to your fellow colleagues and doing group work on this and submitting all of the data at once for classification?
A part of me would like to say yes, but well, the thing is when you work with such a large group of very, highly well-respected scientists, everyone has their own opinion on some stuff, and sometimes trying to manage and organize that many people, there's some mediation that's involved to some extent. So it was a good eye-opening experience for me to sort of learn how to be in that managerial role with this sort of process. Would I like to do it again? Not really anytime soon, to be honest. It really took a lot of work out of me. I had a lot of sleepless nights trying to coordinate stuff and do it. There were over 100 emails in our group chat, and I think I wrote like a third of them almost. So
Wow.
it was a great organizational role. I'm very happy for everyone that I worked with. Everyone helped out. But combining working with that many people and then having to work with gathering all the information and making that large stream field map. I'm happy to just be the person that someone sends a piece to. I do some SCM work and then I send it off to someone else and they write it and they put me in there too, because it did take a lot of work. But the other thing I like to say with that is in the case of Ohio, it was one of those cases where the meteorite fell in a state that there was no known repository or no known classifier from that state that worked on it. So what tends to happen is if a meteorite fell right now in New Mexico, I would completely back off because University of New Mexico is right there. They have the capabilities, they have the instrumentation. If a meteorite fell in Arizona, ASU is right there. A meteorite fell in Houston. I backed off because we have Rice University right there. You had NASA Johnson Space Center. If a meteorite fell in Portland, I would hope that someone across the globe or someone else in the US wouldn't try to speed run a classification before our group did. And if a meteorite fell in my hometown in Miami, Florida, I would hope that I'd be able to work on that one. But that one's since I don't live there anymore, that's kind of a toss-up. But yeah, we try to make sure we don't step on each other's toes. So if it falls very in one person's state, I'd like them to take charge of it, ideally.
Great. Thank you.
That's fantastic. Thanks for explaining that too. I really appreciate it. If you had told me this is we're pulling up to the end of episode 11 from the lab with Daniel Sheikh. If you had told me 5, 6, 7 years ago that we'd be doing this together and that you would be the one reaching out to put that workload on your lap and like tapping all the people you look up to or proud of or people who have done this for years and you're the new kid on the block, to reach out to them and say, hey guys, I'm going to be coordinating this. I got it. Kudos for you, man. Well done. And it shows how respected you are in your community, regardless of your age.
No, thank you, Topher. Really appreciate it. It's my two goals, like I said, were for this classification were I want to make sure that, we did something, maybe something unprecedented has been done before, but something that all the classifiers would feel like they were involved, but also involving all of the finders, the hunters, the dealers, so collectors. So I did a lot of reaching out through Facebook, just messaging everyone that I saw. If I saw someone find something, I messaged them. If they didn't find something, I still message them, just asking if they know who found stuff. And I did get a lot of help from several collectors who were feeding me information here or there, or like, oh, this person just found a piece. You should quickly message them on Facebook, and then I do, and then I get more information, or et cetera. So I think probably the biggest thing that led to this classification being a success was the fact that there was a clear and transparent connection between the people who found the stones, the people who knew who found the stones, the people who were doing the scientific write-up, and then ensuring that everyone was involved to some degree in the process. So it's like we all felt that we brought something to this, and that I think is, I don't know if it can be replicated again to this level, just because of the effort of how many people actually went out to find pieces. But if there's one that falls in Oregon and a bunch of people go out, I might go out. I mean, I've only tried hunting one time in Florida when I was I think Mike Hankey, he sent me like some radar of something that fell over Perry, Florida. I think Michael Farmer had like a funny photo where he posted a picture of something that he said was from there, but it wasn't. I went there and I got permission from this landowner to search their farm, and I didn't find anything, but that made me realize, just how much of a difficult job it is to actually go hunting. And Matt Stream has told me so many stories. Pat has told me so many stories about hunting, and maybe someday if something falls near Portland, I'll try that.
Your time is better spent behind the scope. I'll tell you that right now.
Maybe a little bit.
Let the grunts go out there and do that. I want to thank you for your time very much. I'd like to open an invitation to anyone who wants to turn on their camera right now. We're going to do the wave goodbye. Daniel, thanks a lot for stopping by for show number 11. Please don't stop. It's a weird number. We need at least a dozen. So come back.
I'll be back for sure. I want to do a presentation on pink spinel orthosite at some point.
Ooh,
The newest rock type from the moon. And
Nice.
I think that would be great to have on your channel. So I'll come back for that one.
That's number 12 then. Come back. All right, everyone. Wave goodbye. Thanks a lot for joining us.
Thank you, Daniel.